Hello, in this video you will be learning how to create a page table manager so that we can map virtual memory to physical memory in a very easy way. Let's get started. So to get started in this video, I just wanted to cover a little bit of information that you should know before you actually start coding a page table manager. From my experience and the experience of many others I've spoken to, making a page table manager is quite a difficult task, so I just wanted to explain what paging is and how it's achieved. So paging on an x86_64 system is just a way for the CPU to access memory that we wouldn't normally be able to access in a way that makes sense. This is done through the mapping of virtual memory to physical memory addresses, and the translation is done via the memory management unit, which is a part of the CPU. This makes it very easy for us to write code, as we can just treat the virtual memory addresses as normal physical memory addresses, and the translation is done for us. The memory management unit uses a page map to be able to translate the virtual memory addresses to physical memory addresses. On our systems in 64-bit long mode, the page map is set up in 4 separate tables. Each table contains 512 entries which point further down the page map. The first of those entries is called the page map level 4 table. This page map level 4 table contains 512 entries which point to page directory pointer tables. Now I'm only going to show 3 entries here because drawing out the entire of the 512 entries is probably a bit outside of the scope. But after the page directory pointer table, we go further down and access the page directory table. Just like the page map level 4 table, there is 500 entries, so as you can see, we now have the page directory pointer table pointing to all 512 of our page directory tables. Now each page directory pointer table can hold 512 entries, so that can create a lot of entries for us to use. Even further down the line, we have now the page table. The page table is the last table that we're going to be creating for the page map, because after the page table, we only have the page entries. So the 512 entries inside of the page table don't point to a further down page table, they point to the individual pages. Alright, so after we've traversed down the entire page map from the page map level 4 to the page directory pointer table to the page directory table and finally to the page table, we can finally access the pages and set the data so that the memory management unit can know how to translate the physical addresses into virtual addresses. Inside of each page entry, it contains a structure that the memory management unit can use to know various attributes about the memory segment and the address that it contains. This is the general layout of the page entry. We have the address of the page entry, which is the physical address of the memory segment that we want to translate into virtual memory. The virtual memory of the page is dictated by its position in the page map. So for instance, if we have an index of 0 in the page map level 4, a 0 in PDP, 0 in PD, and a 0 in P, then the virtual memory address will be at 0. Whereas if we had a index of 1, so we went to this page instead of this page, then its memory address will be 0x1000, this page will be 0x2000, so on and so forth until we get to the second page table, and then the virtual memory addresses just keep on increasing from there. But the physical memory address that it's translated to is stored in the page's address variable. The address value is only 52 bits wide, because each page is aligned on a 12-bit boundary, so that's a 0x1000 byte boundary, which means we don't need to use these extra 12 bits, and that is handy because we can now apply those to separate attributes so that the memory management unit knows what to do with this memory. These attributes include things such as, is the memory readable or writable? Is the memory present? Or is the memory using a cache, for example? There's a multitude of different things that we can use in this attribute section. The structure for the page table entry to point to the next page table is very similar to this page structure entry here. So we have this address here, and when it's used as a page directory, instead of pointing to the physical memory address, this address here points to the physical memory address of the next page table. And the attributes is fairly similar as well. Now this 3-bit section here that we have here, it's available bits for us to use. So like if our operating system needs to keep track of some specific operating system implementation that we've made, that's where we can store the bits for each page. Alright, so I think I've covered enough information on how the page map works and how it's structured, so let's get into making the code. Alright, so now let's get started making our page table manager. Now the first thing I want to do is clean up our source directory a little bit because we're going to need quite a few paging files. So we'll create a new folder and we'll call it paging, and we'll move everything that has to do with paging into there. So we'll put page frame allocator and the source for page frame allocator. And now we need to make sure that when we include page frame allocator, we do paging / page frame allocator.h. Inside of page frame allocator.h, whenever we need to access something that's outside of the paging directory, we just need to do .. Alright, so we'll fix up all of those. So we have .. EFI memory, bitmap and memory, and kernel.cpp is including paging / page frame allocator. So we can just test that to see if we've broken anything, but if not, it should be all good. So as you can see, we have the exact same result as last time, so now it's all working well. We can start making some new files for our extra paging functions. Now the first one we're going to make is just called paging.h, and this is just going to contain some simple structs that we're using to manage the page table. So inside of paging, the directory, we can create a new file and call it paging.h. Inside of paging.h, we do pragma once. And now we need to include standard int. So include standard int.h. Alright, now we need to declare our struct for the page directory entry. Page directory entry, curly brackets. Now we're going to use bit fields to fill this in because of how I explained in the theory section of this video. We have several bools that are stored in singular bits that we need to access, and we also need a very large value that we use to store the address, and all of this is stored inside the same 64-bit value. So we need to use bit fields. So the first one is bool present, and this one is the size of 1, so we'll do :1. Bool read write, and this is :1 as well. Bool user super. And all of these are just attributes that the page directory has. Or if it's a page entry instead of a page directory entry, it's attributes that will be passed to the page instead. So present means the page that the page directory entry is pointing to, or the page directory that the page directory entry is pointing to is present. It's there. The memory management unit can access it. Read write, we just make sure that the page that is in question can be read or written to. User super defines whether the memory in question can be accessed only by the supervisor or by both the user and the supervisor. Now this has to do with privilege levels. We have bool write through. Now for most of the rest of these, I'll leave a link in the description if you'd like to read up about them, but I'm just going to be touching on the ones that are relevant for this video. Bool cache disabled, bool accessed. Now this accessed bit gets set to 1 whenever the CPU accesses this page in memory. That can be useful for various things. We have a bool ignore 0, which is also 1 bit in size. Now this is just something that we ignore. We can't use this. That needs to be reserved. We have a bool larger pages. Now this one is really important because what it does is it turns the next page directory entry into a page of the size of all of the page entries that the page directory entry would have held, if that makes sense. So a page table can hold 512 pages, which is 4096 times 512 bytes. But if this is set, and this is pointing to a page table, then that page table will act as a page of the size 512 times 4096. If that makes sense. We have another bool, ignore 1, so we need to ignore this one as well, it's reserved. We have a uint 8 available. Now these are just 3 available bits for us to use. They're not reserved. We can store anything we want in them if we need extra attributes for our page table or anything like that. We have the uint 64t, which is the address, and this is the last bit field that we need. The address will be of size 52. Now the sum of all of these bit fields needs to equal 64 bits, so that this page directory entry struct is only 1 64-bit in size. Alright, and one more struct we need to declare is called the page table, so we'll do the struct page table. And we have page directory entry entries, and this is of size 512. So the page table holds 512 page directory entries or 512 pages. Now we'll be able to discern between page directory entry and pages when the time comes. We'll just cast it to whatever we need it to be. And the page table needs to be aligned, so to make sure that that happens, we'll do attribute aligned by 0x1000. Right, now we've defined the structs that we need for our paging, we can go on and create the page map indexer. So the page map indexer is a class that I've made. It's a utility class that converts a virtual memory address into the indices into the page map that we'll need. So we'll create a new file and call it page map indexer.h, and we'll create one called page map indexer.cpp. Now this doesn't need to be a class, I just like it to be a class because I like classes. You can use structs if you need to. So inside of pagemapindexer.h we need to include our pragma once, and we need to include standardint.h. Now we can define our class, so the class is pagemapindexer, curly brackets, and our public tag. We need a constructor, pagemapindexer, which takes a uint64 virtual address, and we need 4 variables, so all of them uint64 pdp underscore I, so this is the page directory pointer index. So that's the index we use inside of the page map level 4 table to find the resulting page directory pointer. The next is the page directory index, the next one after that is the page table index, and the next one after that is the page index. Alright, now we can go on into the implementation of that, so we'll jump on over into pagemapindexer.cpp, and we need to include pagemapindexer.h, and we need to do the implementation of our constructor. So we'll do pagemapindexer, pagemapindexer, uint64t virtual address. Alright, now we need to do some bit shifting. So we need to bit shift virtual address to the right by 12 bits. We need to do that because all of the addresses in each page are 12-bit aligned. So all of them are aligned by 4096 bytes. So bit shifting to the right by 12 bits solves this issue. Actually, this needs to be bit shifted to the right and equal 12. Now we can set our page index, so p underscore I equals virtual address and 0x1ff. Now we need to AND by this bit mask so that we only get the part of the virtual address that actually corresponds to this page index. Then we need to bit shift the virtual address again, so bit shift to the right, but we're bit shifting by 9 bits this time. Now we can just copy the last 2 lines that we did and change PI to PTI. Do it again, change PI to PDI, and one last time, and we change PI to PDPI. We can get rid of that last line there. So we're bit shifting to the right by 12 bits, getting the page index, bit shifting it to the right 9 times, getting the page table index, so on and so forth. Now we can jump back on over into kernel.cpp and test this out to see if it is actually working. So back in kernel.cpp we can get rid of all of this rendering detail that we have here. We don't need that anymore, and we can get rid of this commented out code. So all we have left is our basic renderer being declared. We have our memory map entries, our page frame allocator, and the locking of the kernel pages. So now we need to include our new page map indexer class. So include paging /page map indexer.h. Now we can create an instance of our page map indexer. So page map indexer page indexer equals page map indexer, and we can give it a virtual address such as 0x1000, which should give us a page index of 1. Now we can print this to the screen, so we'll do new renderer.print to_string page indexer.p_I. So we'll print the page index. And now I will print a space, a hyphen, and a space just to discern between the different indices. And now we can just copy this line 3 times. Get rid of the last one and change PI to PTI, PI to PDI, and PI to PDPI. Alright, now building that, we can see what indices we are given from this virtual address. Now, as you can see at the top left of the screen, the first index that has been displayed is the page index, and with a virtual memory address of 0x1000, this is correct, as it is the very first byte of the second page in memory. Now we can do something like 0x1000 times 52 plus 0x5000 times 7. And we'll see what that gives us. Actually, we'll change it to 5 with 4 zeros, and we'll see what that gives us. Alright, so as you can see, our page map indexer has given us a page index of 100 and a page table index of 1. So this means that we are accessing the second page table and the 101st page within that page table. Alright, now we can get onto our page table manager, which will actually be manipulating these page tables from the information that we give it. So to do this, we need to create another class. Now, I know with page frame allocator, it didn't need to be a class because we'll only ever have one of these page frame allocators at any one time. However, the page table manager, we will need one for every single page map that we have. So basically every process will have a page table manager attached to it. Alternatively, we can have one page table manager and we just change around some values within it every time we change process. But I'm going to be doing it with a class. So we'll create a new file and we'll call it page table manager.cpp. We'll put it inside of paging. And we'll also create a header file, so page table manager.h. Now inside of page table manager.h, we can do pragma once. And we can do include paging.h so that we have access to the structs that we made. And now we can define our class. So the class is page table manager, and we'll add our public tag. And now we need a constructor. So page table manager, and we'll take a page table pointer to our page map level 4 address. So that's the highest table in the page map. Now we need a variable to store the pointer to this PML4 address. So we'll create page table pointer PML4 address. Now I like using a constructor so that it's impossible for us to forget to define the page map level 4 address, but we'll store it as a public variable just so that we can change it if need be. And now we need one function called void map memory. And we need to pass it two memory addresses, the virtual memory and the physical memory that we want to be mapped together. So void pointer virtual memory, void pointer physical memory. Alright, so now let's get into the implementation of our page table manager. So in page table manager.cpp, we can include page table manager.h. We can also include page map indexer.h, include standard int.h, and last but not least, include page frame allocator.h. So the page table manager needs access to all of the paging files that we made before. So the first thing we need to do is make the implementation for our constructor, which is very simple. Page table manager, : page table manager, page table pointer PML4 address. And now we can do this PML4 address equals PML4 address. Actually, I'll change this PML4 address to just PML4, just to shorten it a bit, make it look a little bit nicer. So this PML4 equals PML4 address. Alright, now we need to create the implementation for the map memory function. So void page table manager, : map memory, void pointer virtual memory, void pointer physical memory, and now our curly brackets. Alright, so now we need to create an instance of our page map indexer so that we can get the indices within the page map. Page map indexer indexer equals page map indexer casted to a uint64 virtual memory. Now we need to create a variable to hold the page directory entry of each page table that we come across. So we'll just create one now, page directory entry PDE. Alright, now to get the page directory pointer from the page map level 4, we need to index into it. So PDE equals PML4 entries indexed by indexer dot PDPI. Before I forget, in pageTableManager.h we need a semicolon after the class declaration. Now we need to create a pointer to the page table, which we will get from the page directory entry. So page table pointer PDP. So the page table that we are currently at is the page directory pointer table. And we need to check if the page directory pointer table is present. If it is not, we need to make one, but if it is, then we can use it. So if not pde.present. If it is not present, then we need to create a point in memory for it to use. Now, our page frame allocator is only currently available inside of the kernel's start function. So we need to create a global instance of our page frame allocator. To do that, just inside of page frame allocator, down the bottom we can do extern page frame allocator global allocator. And inside of page frame allocator.cpp, we need to declare that probably just up the top somewhere is fine. So underneath initialized, we can put page frame allocator global allocator. Now in kernel.cpp, we no longer create our own allocator and replace all references to new allocator with global allocator. Now before I forget, we need to actually instantiate global allocator. So we'll do that inside the kernel start function. Make sure all of these are capitalized. So global allocator equals page frame allocator. Alright, so now back into pageTableManager.cpp, we can use our new global allocator to allocate some memory for our new page table. So if the page directory pointer is not present, and we can tell that by looking at the PDE that we assigned here, we need to make PDP equal casted to a page table pointer global allocator.request page. Alright, so our page frame allocator is coming into use already. Now we need to set all bytes inside of this entry to 0, so we need a memset function. We can define a simple memset function inside of memory.h. So void memset. We need a pointer to the start address. We need a value, so we'll just do a uint8 at the moment. So uint8 value and a uint64, which is the amount of bytes that we want to set to this value. So we'll just set that to num. Now copying this line and heading into memory.cpp, we can paste that, do our curly brackets, and now make a loop. So for uint64 I equals 0, I less than num, I plus plus. And now we can dereference casted to a uint8 pointer bracket start casted to a uint64t plus I equals value. So we're casting start to a uint64 so that we can do normal integer maths on it, casting it back to a uint8 pointer, dereferencing it, and then setting that value to our value. So that's pretty simple as far as memory functions go. Now back inside pageTableManager.cpp, we need to include /memory.h, and now we can use our memset function. So memset pdp 0 and 4096. So the size of one page is 4096, or we can just do 0x1000. Now that we've set the entire page to 0, we can start filling in some values. So our pde.address equals casted to a uint64 pdp bit shifted to the right by 12 bits. So we've got the address, we need to set pde.present to true, because it's now true, because we've made it present by allocating some space for it, we need to set read write to true so that we can read and write this memory. Leave it to false if you just want read-only memory, but we don't want that. And now we need to set the entry in the PML4 to this new page directory entry that we've made. So PML4 entries indexed by indexer.pdpi equals PDE. Alright, so now we have created a new PDP for this page table if it is not present. Now we need to just check if it is present, so else PDP equals casted to a page table pointer, 2 brackets, uint64, go out of 1 bracket, pde.address, bit shifted to the left by 12 bits. So we're just getting the address that is stored inside the PDE. If it is present, bit shifting it to the left by 12 bits so that we have the logical address and then assigning it to our PDP. Now for the next 2 pages in the page map, we basically do it exactly the same. So we can copy this, paste it again, and change some things. So the page directory entry now needs to equal PDP indexed by PDI. So now that we're getting the page directory from the page directory pointer table, the page table PDP now needs to become PD. And just like the same, if it is not present, we need to create one. So PD equals a new page, memset that, change this PDP to PD, change this PDPI to PD, and change this PDP to PD. Alright, so just copying all of that and then changing all references to PDP to PD. Alright, now we can copy that one more time and change all references to PD to PT. So now we're getting the page table from the page directory table. We need to change this PDP reference to PD and all other PD references to PT. So PD index, PT semicolon, PD equals page table request page, memset our PT, our address equals our PT bit shifted, and our new entry equals PT underscore I. We also need to set this PML4 to be the same as the one we got it from. So up in the area where we get the PD, we can change that PML4 to PDP. And the same here, we change this PML4 to this PD. Alright, so now that we've walked all the way down through the page map, we can now access the page at the end of the maze. Now to get the page, we need to get the entry from the page table using the page index. So our PDE equals page table entries indexed by indexer.p underscore I. Now we can get the address, so pde.address equals our new physical memory, so uint64t physical memory bit shifted to the right by 12. So we're converting our physical memory into a address that the page table can accept. We're setting pde.present to true, pde.read write to true. And now that we've modified the values in our page, we can apply it back to the page table. So page table entries indexed by indexer.p underscore I equals PDE. Alright, so that is done now. To run back through everything, we are getting the page directory pointer table from the page map level 4. If it doesn't exist, we're making one. And then we're getting the page directory from the page directory pointer table, yada yada, getting the page table from the page directory table, and then getting the page from the page table. And of course, if no page table exists along the way, then we are creating one. This PD needs to be a PT. Now to test that out and make sure everything's working, jump back into kernel.cpp, get rid of this printing stuff, get rid of this page indexer instance. So what we're going to do is create a new page map for our kernel to use, one that we know exactly what's going on. We could use the one that's provided by UEFI, but it would be preferable to know exactly what's going on, so we'll create a new one. So to begin, we need to create a page map level 4, so page table pointer. Let's just include paging/paging.h, so we have access to this page table. So our page table PML4 equals casted to a page table pointer global allocator.request page. So we've created some space for our page map level 4 table. We need to memset the entire page of this page map to 0. So PML4, the value is 0 and the size is 0x1000. And now we need to create a page table manager that takes our new page map level 4. Page table manager, of which we need to include the class for. So include paging / page table manager.h. So our new page table manager, let's just call it page table manager, original name I know, equals page table manager with our PML4 as our new address. Alright, now to keep using our kernel as we have been, we need to identity map the entire span of memory, just like UEFI did for us. So this is pretty simple. For uint68t, t equals 0, t less than get memory size, boot info memory map entries, boot info memory map descriptor size, t++. Actually, not t++, t plus equals 0x1000. So we're going through each page in memory and mapping it, identity mapping it, so each virtual memory address corresponds to each physical memory address. So page table manager dot map memory casted to a void pointer t, which is the address, and then we need another casted to a void pointer t, so virtual memory equals physical memory, and that's it. So we've gone through all of memory and mapped it, identity mapping. The next thing we need to do, which UEFI did for us, is we need to make sure that our frame buffer is still mapped in the address that it was. So we need to calculate the base and the size of the frame buffer. So uint64t fb base, frame buffer base, equals casted to a uint64 boot info frame buffer base address. Now we can get the size, uint64t fb size equals casted to a uint64t boot info frame buffer size plus, and we'll just do this so that we actually have enough space for the entire frame buffer, just so that we're not allocating a little bit under what we need. So we'll just add an extra page on the end, so plus 0x1000. And now, just like up here, we can identity map the frame buffer as well. So for uint64t, t equals fb base, t less than fb base plus fb size, t plus equal 4096. And now we can just copy this page table manager.map memory function. There shouldn't be a semicolon here. I accidentally put a semicolon, there should not be one. Alright, now that we've made our new page map, we need to load it into the CR3 register, which I will do with a little bit of assembly. So we'll do a ASM tag, quotation marks, move, %0, comma, %, CR3, end of quotation mark. So we're moving our value into the CR3 register. Now we need 2 colons, quotation mark R, bracket PML4. So what this means is we're putting PML4 into the register 0 and then executing this command. So we're moving our page map level 4 into the CR3 register. So that means our memory management unit will be using our new page map instead of the old one. Just to test if it still works after we apply the new page map, we need to print something to the screen, because if it hasn't worked, then we won't be able to print to the screen because we can't access this frame buffer memory. So what we do is new renderer.print, I'm in the new page map. So now we can make that one, build that one, and now as you can see at the top left of the screen, we have successfully printed using the frame buffer of the new page map, which means our memory mapping functions are working properly as they should be. Now the next thing we can do, just to explore the possibilities of virtual memory mapping, is we could map a section of memory up really high, like 7 with 8 zeros after it, and then map it to a physical address like 0x3000, change the value in 0x3000, and then read it from that really large address. So let's do that. Back in kernel.cpp, we can just comment out that for now, this print line. Now we can do something like this: page table manager.mapMemory void pointer 0x600000000. And as you can see in decimal, that is a very large number. That is 25 gigabytes. So that is much larger than our QEMU system would be able to handle. So we are only able to access this memory address that's so high because we've mapped it to a physical address that we can reach. And that physical address in this example, we'll just do something like, just to avoid all of the pages that we've already allocated, we'll do something like 0x80000. Now we can create a uint64t pointer test equals casted to a uint64t pointer this value. If we dereference that test variable now and set it to something like 26, we can now read from this physical address and it will display 26 because we've set it to this virtual address, which is mapped exactly the same. So now we can uncomment this print line and change this string to a toString dereference test. Now, as you can see at the top left of the screen, we are displaying a 26. So that means we've successfully mapped our virtual memory to a different memory address. There is a ton of optimizations we could do with paging in any form, and I might actually explore those in the next video. But for now, we've created a page table manager that can successfully map any virtual address to any physical address and vice versa. So that's pretty good, I think. Alright, that's it for this video. Thank you for watching and I will see you next time.